these topics where you never stop learning, and so there's this material could continue forever. There's no end to it. But I have a few topics here that build on what we've done on path integrals that I hope to make it through today, that just give you a little flavor of some of the things to do. So one of the first ones I want to do is path integrals and quantum stat mech. Okay, and I'll do this in 2 steps, as often the case here. We do quantum mechanics first, and use our framework to develop stat mech. It's actually a pretty close connection. So remember, we started with this propagator. It was d of xf, some tf, xi, ti, which was the transition from some initial position to some final position governed by the Hamiltonian. Okay. And we wrote a path integral for that. So I'm going to come back to writing the path integral. But let's just first play with this. Well, experimenters, of course, limited to time. We're up there where that's time. If you want to be a theorist, you can say, well, we can play games with that. We can take that and analytically continue it to imaginary time. So we've done that a couple of times already. So if we take t goes to minus I tau, then this thing looks like e to the minus I h t turns into e to the minus h tau. And so if you take the initial time to be 0, the final time to be beta, so we're just playing with this thing, where beta is 1 over kt, or 1 over t. Boltzmann constant is, of course, 1. Then this ends up being you end up with xf e to the minus beta h xi. Okay. Well, that's the coordinate space representation of the density matrix. So rho hat is e to the minus beta h is the density matrix. Okay, remember the density matrix is defined in the canonical representation, canonical ensemble, because you're treating beta as your parameter, temperature is your parameter there. So this is in the canonical ensemble, and e to the minus beta h. Okay, this is the coordinate space representation. Okay, and so if that's the density matrix, you can easily get to the partition function. Okay, the partition function is trace of the density matrix e to the minus beta h. And so what does trace mean in this case? Well, it means you take x final equals to x initial, so xx e to the minus beta h, and sum over those elements. So it becomes the integral d3x x-axis e to the minus beta h. Okay? So to do that, you have to identify the final position and the initial position, xf equals xi, or really x of beta, tau equals to beta is x of 0, or so this is periodic boundary conditions. Okay. So just playing games with our beast to begin with, we see that while this initially had this interpretation of taking something at position xi ending up at position xf at a later time, if we play this game, we make it periodic, so it comes back to the same point, and we sum over all of them, we get the partition function out. So that game has been worth it. Okay? And so if we go for a path integral representation, well, we have a path integral representation for what we have above. We just have to do the same trick. Okay? So what we previously had in the path integral was the action, and the action now turns into, well, it was the integral over time of the Lagrangian. Let me just write the answer and you can sort of see it. There's minus integral d tau from 0 to beta, so the time goes from 0 to beta, and it's 1/2 m d by d tau squared plus v of x. Okay, you know, to start with, it was d by dt minus v of x, but then t goes to I tau. There's an extra minus sign here, so these carry the same sign, and I pulled the overall sign out in front. Okay. So this results in the partition function has this path integral representation dx tau, integral over all paths, e to the minus 0 to beta d tau 1/2 m dx d tau plus v of x. Okay, with x of beta equals x of 0. Okay, this is the famous Feynman-Katz formula. Okay, and so, well, I could go on about how we use this. I'm going to go into field theory. But I do just want to make one observation before I go on, and that's as t goes to 0, then beta is going to infinity, and that's like time going to infinity, except we've gone Euclidean on it. Well, what's the physics of temperature going to 0? That's going to the ground state. When temperature is non-zero, you get the excited states, but at 0 temperature, you just get the ground state. And that's just like we did in our functional methods thing. That's just the same thing that we got by projecting out the ground state by taking the time interval to infinity. Here, we've regularized this just by this Euclidean trick, There we did an I epsilon trick, but it's the same result. Okay. If I do quantum field theory, let's do the same thing with quantum field theory. The transition again is xi of t goes to phi of x and t. We'll again take t goes to minus I tau. We'll analytically continue. We'll take a finite time integral, 0 is less than tau, less than equal to beta. And if you just do this, you take the Lagrangian plus j phi, it goes over to minus, I'm going to do the scalar, d phi d tau squared minus del squared phi, del phi quantity squared minus v of phi plus j phi. So as you see, all these pieces here, this is d by d tau, that looks just like the Hamiltonian, right? That looks like minus h. And so we would write this as minus, well, you could write it as h, or let's just call it L Euclidean minus j phi. And the partition function then is z of j is integral d phi e to the minus 0 to beta d4x L Euclidean minus j phi. And we have to choose then periodic boundary conditions. Phi of x tau equals beta is phi of x tau is equal to 0. Okay, so what we've got here, it's actually an amazing thing. So what we've shown is that 4-dimensional Euclidean quantum field theory on this finite interval. So you just take the quantum field theory on this finite interval with periodic boundary conditions equals quantum stat mech in 3 spatial dimensions. Okay. Remember, so time is not an important variable in stat mech because everything's equilibrium. So time doesn't play any role. So the only thing that you need are the 3 spatial dimensions. Tau has turned, the time variable has turned into the temperature. It's an amazing equivalence. And again, note that as t goes to 0, the partition function turns into what we call the generating function. Okay, so basically that interval then extends to infinity. You get an infinite time interval, and you end up back with the ground state. Okay. So that's almost all of it. Basically, I mean, it's not really almost all of it, but it's the foundations. But the one thing I do want to tell you about is the propagator. Okay. So having that partition function, we can do perturbation theory as before. And so if you look in advanced statistical physics problems, you end up developing the same thing with all these Feynman rules using Z of J. So if you want to know transitions or whatever, you can get all of them. The Feynman rules are the same. Yeah, at least they're related. Okay, but the propagator changes. So the difference is the propagator. Okay. And the propagator is different because you need to have these periodic boundary conditions. You need phi at x tau equals beta is phi of x tau equals to 0. Okay. Well, that's not that hard. Everyone knows how to do these periodic boundary conditions. You then use a Fourier sum with e to the minus I omega n tau with omega n equals 2 pi n over beta. Okay, so we're doing a Fourier sum with a discrete set of things. Okay, and we can develop the propagator. I'm probably going to take a little bit of a shortcut. Basically, what you want is minus d squared d tau squared minus del squared plus m squared. So I've changed the sign on the timepiece times this propagator, which I could call d beta, is delta of tau, x and x prime, tau minus tau prime, delta 3 of x minus x prime. Okay? And you do this by imagining that you've got d beta of x is, well, spatially it's the same, d3k over 2 pi cubed. We then want the sum of n, and just for convenience I'm going to put the time t there. E to the plus I omega tau e to the I k dot x, some g of omega k. Okay. And so this t here is like when you do the Fourier sum, L, the distance across some finite region. And if you just apply that and look for a delta function, you get g of omega k is 1 over omega n squared plus k vector squared plus m squared. So it looks just like what you'd expect. You take two derivatives there, two derivatives there, plus m squared, you cancel this. This Fourier sum with this replaced by 1 gives you a delta function if that t is there. Okay, so the transition to the propagator is, so if we had the continuum propagator would have been d4k over 2 pi to the fourth e to the I k Euclidean dot x over k 0 squared plus k vector squared plus m squared. That turns in to, at finite temperature, T sum over n integral d3k 2 pi cubed e to the I omega n tau e to the I k dot x over omega n squared plus k vector plus m squared. Okay, so really this equivalence is, as t goes to 0, this is dk0 over 2 pi. Okay, and you can show that, a little more precisely. But remember, as t goes to 0, this becomes a small thing, so this sum becomes close to being a continuum, and then you work at it, you get that's the correspondence. So everything goes the same, except in the Feynman rules, you have the propagators equal 1 over omega n squared plus k squared plus m squared, and integral d4k goes to 2 pi t sum over n integral d3k. Okay, so that's the correspondence. Okay, so this is what's called the imaginary time formulation. It's the most common one. There's also a real-time formulation, but I'm not going to do that. But the imaginary time ties in beautifully with this path integral. Okay. Questions about that? That's topic number 1 for the day. Okay. No. Topic number 2 is effective field theory 101. Okay, 101 is just used to indicate that we get partway into the topic, but I don't do everything. But in particular, the piece I will do is the idea of integrating out fields. The phrase integrating out. Okay. So, effective field theory is a technique. It's just usual field theory, but it typically implies that there's 2 sectors of the theory, one of which is heavy and one of which is light. So the idea in words is, if you imagine a theory that has some fields being heavy and some fields light, so there's some scale where you do the separation. At low energies, you're only going to use the light fields. Okay. So the heavy fields appear only in loops or in propagators, internal stuff. They don't appear as external states. And so the idea is that you do the path integral over the heavy fields. And they then disappear from your theory. But there's some residual effects in an effective Lagrangian. And then, having done that, you've still got all these light fields around, and you do field theory with the light fields. Okay. So it's not that you're changing your theory. Your effective field theory is just usual quantum field theory, except that you're doing it in a different order than usual. Rather than taking all the fields and doing a calculation involving all the fields, you do some calculation ahead of time where you get rid of the heavy fields, leaving all the residual effects categorized in this effective Lagrangian, and then you use that plus the light fields to do field theory with the light fields. So instead of doing everything at once, you do this two-step process. Okay, so I want to go through that process with you and give you a couple of examples. So here's formulas. Let's imagine we have two fields, phi and chi. Okay, and I'll take the phi to be the light, and I'll take chi to be heavy. Okay. So the Lagrangian then of these two fields, phi and chi, well, there'd be something, let's call it L0 of phi. There'll be some piece that only depends on chi, and there'll be some interaction piece between the two that involves phi and chi. Okay, so this piece here could just be 1/2 d mu phi squared minus some v of phi. So there's some interactions there. The other stuff, this one could be similar. This guy could be, for example, it could be chi phi squared. That's an example I'll do. It could be chi squared phi squared. So those are typical types of interactions. Okay. So in complete generality, the full theory is defined by this path integral, let's call it z of j phi, j chi, which is the path integral over phi and over chi. Either the I integral d4x L0 of phi plus L0 of chi. I actually don't have to write all these guys out. Plus Li, but the piece here is j phi times phi plus j chi times chi. Okay. So there's the full theory, everything there. But now if we're working at low energies, we want matrix elements of the light fields. Okay, so we have this Green's function, some Green's function of phi, dot, 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 is minus I to the n delta z over z of 0 psi of j phi of x1 j phi of xn. At the end I'm going to set j phi is equal to 0. Okay, but I left the argument there out, but let's just put it back in. This argument here is a function of j phi, but j chi is set equal to 0, right? There's no j chi because there's no derivative with respect to it, and at the end you set all the j's equal to 0 anyhow, so you can just set that equal to 0 from the start. Okay. So here's what we got. Then z of j phi and 0, the thing that's relevant for us is, let me write it out in two ways. There's in two steps. There's the integral d phi over here, and I'll write the integral d chi over here, and I'll take all the stuff that has chi and make sure it sits on that side of it. Okay. So over here I have e to the I integral d4x L0 of phi plus j phi phi. That's that piece. And then the stuff that depends on chi is e to the I integral d4y L0 of chi plus L interaction of phi and chi. So everything's not completely separated. This stuff doesn't depend on chi, that's good. This stuff does depend on phi though. Through the interactions there's the phi piece. So I can't just throw that away. I have to write this. Okay, this is e to the I some w of phi. That's a functional of phi. Now, so if we can write e to the I w of phi as something that goes like, e to the I integral d4x L extra of phi. Okay, so something, anything, but if it can be written in that form, then we have z of j phi is integral d phi e to the I integral d4x some L effective plus j phi, where then with L effective is L0 plus L extra. Okay, so there's the process, the ideal process in formulas. At low energies we take this, we integrate out, so there's the step that's called integrating out. And you're left over with something which I've called this L extra. And then this now becomes an effective field theory. Here's my effective field theory. It's an ordinary field theory, just like we would have written down, but with the changed Lagrangian, where the Lagrangian is now this effective Lagrangian that takes the usual piece plus whatever comes out from the integrating out part. Okay. So the philosophy is that, and the physics input that's crucial now is if chi is heavy, then you can always write a local Lagrangian. Local effective Lagrangian. And the physics behind that is the uncertainty principle. So that delta x goes like 1 over delta E, which is very small if we have a heavy enough field. Okay. So there's the physics. The converse is also interesting, though. If chi is light, you cannot write an L effective. It's then strictly non-local. So this, by making it local, is just the uncertainty principle here. This thing, anything that happens here, can be written as a local thing. If chi is light, then you can't write it as just a function of one position. You have to write it as a function of two positions, or more positions, lots of positions. So it's non-local. And maybe that's going to be more obvious in the example I do next. But it's certainly, that's the physics distinction. Okay. So the example. Let's take a linear coupling. What I mean by linear coupling is I'm going to take L interaction, that's a function of chi and phi, to be chi times some function of phi. Okay? Typical one is phi squared. Okay? But it could be phi cubed, it could be other things. Okay? So instead of the general one, if you had chi squared there, or higher powers, it's a little harder to do, though we can talk about how to do it if you want. So then L0 of chi plus L interaction of chi and phi is, that's 1/2 d mu chi squared minus m squared chi squared plus chi f of phi. So that's the piece that I'll do. That's the easy one to do. And so then what I've written is e to the I w of phi is integral d chi e to the I integral d4x. Well, it's that piece. So let's just write it L0 plus chi f. Okay. But that's just our Gaussian integral. Where we had j before, it now goes to f of phi. So we know the answer from our doing this Gaussian integral before is some normalization which we don't care about, e to the minus I over 2 integral d4x d4y f of phi at y let's make it at x here, sorry. At x, Feynman propagator of x minus y, f of phi at y. So there's our general result for this. So again, if f was phi squared, there'd be phi squared at x, phi squared at y, and this propagator in between. Okay, well, there's the example where it's not local at this stage. Okay, if this were, for example, the photon propagator, then this goes like, well, it has a long-range component. It's like 1 over x minus y absolute value. But to put this in a local form, okay, let me actually write it on the next page. I have df x minus y is integral d4k over 2 pi to the fourth e to the minus I k dot x minus y k squared minus m chi squared plus I epsilon, of course, okay, which is the same starting stuff, d4k. But then I'll write this as minus 1 over m chi squared. So we're imagining that this chi is a very big number, minus k squared over m chi to the fourth, plus dot dot. So this is m large. And we can then pull that outside in front of the integral. So it's minus 1 over m chi squared plus box over m chi to the fourth plus dot dot dot. Of on integral d4k over 2 pi to the fourth e to the minus I k dot x minus y. Okay, so I've traded k squared for box acting on e to the I k dot x. But of course, that just brings down a factor of k squared, so that's equivalent. But then this is the delta 4 of x minus y. So now this looks local. And our w of phi is minus a half integral d4x. Okay, so I'll use the delta function to get rid of the d4y. And it ends with minus 1 over m chi squared f of phi squared evaluated at x plus then 1 over m chi to the fourth f of chi squared box f of chi squared plus dot dot dot. Okay. So this is my L extra, and it is local. Okay, and you can see from this that the criteria for this is that the chi be heavy if m chi were 0, for example, you couldn't do this trick, so that would not make sense. And if derivatives appearing in the physics are of order m chi, this series never converges. So if you were to try doing this when m chi was non-zero but small, then this series is useless, because when you take matrix elements, derivatives are bigger than m chi, and that series is useless. So this is an effective thing to do, like effective field theory, when m chi is big. Okay. Let me do just a concrete example. I'll do it quick. I actually have plenty of notes on it, but I think this is from a previous class where we did Goldstone bosons. It's actually in calculating 4. I looked it up. If you want to review your notes, which was March 11th. Okay. But this was the idea where the case where we had two fields, v of phi 1, phi 2, which was minus mu squared over 2 phi 1 squared plus phi 2 squared, lambda over 4 phi 1 squared plus phi 2 squared squared. And the ground state was, let's take phi 1 was v, the square root of mu squared over lambda. And around this point, we expanded it and found that m1 squared was 2 mu squared and m2 squared was 0. So there was our Goldstone boson. Okay, so you've been doing this again in the homework. What we did back then, which was a long and painful calculation, was we did the scattering amplitude. By using Feynman rules. So we had the Feynman rules, we did all the scattering amplitudes, and there were lots of cancellations. Okay, and I used that as a lesson back then. By changing the field names, I could make the calculation easier. Well, here's another way to make the calculation easier. We can just take the heavy field, which is phi 1, phi 2 is the light field, so phi 1 is our chi, phi 2, no, I'm sorry, phi 2, all right, here we go, get out of there. Phi 2 is what we call phi, is our light field. And I can integrate out the heavy field and get the effective Lagrangian for the case, for the scattering amplitude. And we'll see the cancellations then are obvious even before we start. Okay, with a little bit of work, we take the interaction Lagrangian chi to be lambda v chi phi squared plus stuff that doesn't enter. Okay, so this is, remember you expand this out. There's the mass terms. There's this cubic piece which goes like that, and there's stuff that doesn't contribute, which I could write out. Okay, so from the work that I just did, then I just take w of phi is minus a half integral d4x Well, it was minus 1 over m squared, which is 2 mu squared, and then f of phi would be lambda v phi squared, but then I square it. Okay, so lambda v phi to the fourth plus 1 over 2 mu squared squared lambda squared v squared phi squared box phi squared. Okay, so what I've done is I've got a piece that goes like lambda phi to the fourth, like phi to the fourth, and a piece that goes like phi squared box phi squared. Okay, if we look at the factors here, I have there's a lambda squared v squared. V squared is mu squared over lambda. So when I take v squared, I get the mu squareds are going to cancel that mu squared. I've got a lambda squared divided by lambda, and I've got a quarter. This is d4x plus lambda phi to the fourth over 4. And the last piece, if I look at it, is if I work at it, let's not do that. Lambda over 2m chi squared phi squared box phi squared. Okay. So our L effective of phi is, well, there's L0, which is 1/2 d mu phi squared minus lambda phi to the fourth over 4. And now I add this new piece in, which is plus lambda phi to the fourth over 4 minus lambda over 2m chi squared phi squared box phi squared. And here's the cancellation that we found out painfully by doing this long calculation before. No, it wasn't that painful, but it's basically we took the scattering amplitude plus scattering amplitude with what I'm now calling chi, exchanged in all possible ways. And there was cancellations there that if you did it right, you could find. Here, you've already seen the cancellation at the effective Lagrangian level. And this guy, if you just take this, yields the scattering amplitude directly. Okay, so we've simplified our life. The cancellation happened once and for all, and we never have to deal with it again. In this case, this is such a simple example that it wouldn't have been that hard to do this and find the cancellation. But here, in more complicated cases, the fact that you can get all the right behavior early on is useful. Okay. So that's my little bit on just plain old effective field theory 101. Questions? Anybody? No. Last topic, and I think timing will be right, is which builds from exactly that, is the Wilsonian approach to the renormalization group. Okay, the Wilson in this case is Ken Wilson. Who got a Nobel Prize for basically this material. And it's going to start off seeming very, very different from our other treatment of renormalization group. But it's going to end up being in the same place. And it's an extremely important concept, especially in condensed matter, but also in particle physics. It's based on this idea of integrating out. Okay. So here's the Wilsonian approach. Let's imagine that we've seen that it's easy to integrate out heavy fields. So if you've got a field that weighs a lot, has a big mass, you can integrate it out from your theory and come up with an effective Lagrangian. But Wilson's idea is to not only do that, but to integrate out everything that's heavy, so including the field that you have. So phi in particular, even light fields, have high energy components. With energies bigger than some scale. So I'm going to call that scale lambda here. Okay. And so Wilson's idea is you integrate out everything. All effects beyond some scale. Okay. So you not only integrate out heavy particles, you integrate out the high energy components of your light fields also. Okay. And you then end up with an effective Lagrangian which is applied below the scale, below lambda. Okay, so it only goes up to lambda, but it has all the right effects below that. So there's a picture that goes along with this that people mentally have. Imagine you've got some field and it's got fluctuations in that field. So here's the real thing. It's fluctuating. There's some structure. There's a sketch of a field with lots of fluctuations on all scales. But if you're living at very low energies, you don't really see these little microscopic fluctuations. You just see the broad wavelength. And so his approach will turn this into a field that just has some variation like that, where you've removed the small scale. Okay. And so this is why it's used so much in condensed matter. In condensed matter you often do this, especially as you go close to critical points. You're interested in long scale behavior of the thing. So small scale fluctuations don't matter. You're interested in what does the system as a whole go through a phase transition. That's a big scale phenomenon. So you integrate out the small scale stuff and you're left with the big scale stuff. Okay. Well, here's the formulas for it. So there's the ideas. Here's formulas. Okay. Z of phi is, so we've got Z of j. Sorry, Z of j is d phi e to the I integral d4x L j phi. Okay. The trick is to break this up into d phi momentum less than lambda and d phi momentum greater than lambda. Okay, and then the result gets written as integral d phi k less than lambda of e to the I d for x L effective, which is a function now of, depends on lambda, plus j phi. Okay, and where you take, to get that, you take e to the I L effective is integral d over this, the high stuff, k bigger than lambda, e to the I, the full thing. Okay, so that's the idea. Okay, in perturbation theory, it's easy to do. Non-perturbatively, the easiest way to do it non-perturbatively is to define a lattice, to take a, put it on a space-time lattice, and then use the lattice spacing as your variable. In perturbation theory, the easiest way to do it is the following. Okay, you take all your propagators in your theory, d4 k over 2 pi to the fourth, I over k squared minus m squared, and you just break that integration up into two pieces, d4 k 2 pi to the fourth up to lambda plus the integral lambda to infinity d4 k 2 pi to the fourth k squared minus m squared. Okay. So just whenever so in any calculation you're doing, you split this up and you do this part, do that to get the effect. Now you can see here one of the reasons why it's done a lot, this procedure is done a lot in condensed matter. It's not done directly like this in most of particle physics because this split up isn't Lorentz invariant. You know, you can, if you shift your variables, there's no natural frame where you cut off the energy lambda. You know, if you're in one frame and you have small energy and some boosted frame, it looks like high energy. So it's a little tricky to do in a relativistically invariant way, but this is the thought pattern. And people use the thought pattern a lot and don't use the calculation a lot. Okay, so what do we expect? Well, let's imagine that I was doing some calculation. Let's imagine I'm doing this calculation like that. We would write that as, let's keep the light one that way, plus make the heavy one, maybe make it dotted. Okay, this is the k bigger than lambda piece. So if I just take the k bigger than lambda piece, I'm going to get a delta L, which is some delta m squared that depends on that lambda over 2 phi squared. Okay. Likewise, if I'm do some scattering like this, here I take, both these guys are k bigger than lambda. That's going to have the following form. Well, it will have, I can call it delta lambda, which depends on capital lambda, and there could be some momentum dependence, p1 plus p2 squared, Let me call it delta G6, which also depends on lambda. Dot, 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 dot. Okay, so I just take the result of this. If there's a constant independent of the momentum, I call it delta lambda. If there's a piece that depends on the momentum, I call it delta G6, etc. Okay, imagine Taylor expanding that. This guy is like some change in the Lagrangian, which is this delta G6 times phi squared box phi squared. Okay, just think about it. When derivatives act on two fields, it gives the sums of the momentums of those fields, P1 plus P2 squared. So this Lagrangian would give me that matrix element. Okay, so that L effective that you get out from this, well, there'd be the kinetic energy piece is unchanged. There'd be plus m squared, which would depend on lambda over 2 phi squared, and there'd be a lambda which would depend on capital lambda over 4 phi to the 4th, and there'd be now be G6, which would depend on lambda phi squared box phi squared plus dot dot dot. Okay. So here, even though I've only got one field, but integrating out its heavy components, I get a field theory with the coefficients there depending on the scale. Okay, so this is then starts now at this stage. It's up to now. It's just looked like path integral stuff. Starts now to look like the renormalization group, because now I've got coupling constants that depend on the scale. One of the interesting things, and the difference from the way we did the renormalization group before, is that we also get new operators coming in. And this is a feature of the Wilsonian logic, that you don't just get the renormalizable operators, you get these non-renormalizable operators that enter also. And then the way we treat this, we still do quantum field theory below the scale lambda. So I would still need to, when I'm doing this, I'd still calculate diagrams like this, where this is k less than lambda, this guy's k less than lambda also, etc. So you're going to get 1/2 minus 6i lambda from this. You get some I of s plus I of t plus I of u. So these functions here would now be cut off. So it looks almost like Pauli-Villar's regularization. Okay, all this stuff is finite now because I don't include any high energy behavior. So we've already finited and renormalized to do this. And yeah, let me just do a little bit here. Then our physical amplitudes would be something like this. It would be, I define minus im at s equals t is equal to u is equal to 0 as minus 6I lambda physical. Okay. Then lambda physical, if you just complete the calculation, would be so the lambda of capital lambda that enters into the Lagrangian. So it's this guy up here, the one that enters the Lagrangian. And if I work out what it is, all right, it turns into minus 3 over 16 pi squared, some lambda squared, log lambda over m, the physical mass. Okay, I've skipped a couple steps. Remember, this lambda can be either lambda physical or lambda of lambda to this order. And if you then just invert this, we get lambda of lambda is lambda physical plus 3 over 16 pi squared, lambda physical squared, log lambda over m physical. And that's the same behavior we had previously for lambda of mu in your homework. So that you then get the renormalization group out. Okay. So here's a different logic that takes you through basically the same physics, but here's another way to get the running of the parameters. So pretty different from the way I did it before, but building on this path integrals. Yeah. All right, so I guess I'm going to stop there. I can do more on integrating out, but let's stop there. If you have other field theory needs, come see me sometime. Okay, good. See you.